So we're near the end of the semester, and I want us to make sure that we get through all of our integration. And so we're going to move into looking at finding indefinite integrals using substitution. So when we're finding the antiderivative, sometimes it's impossible to do it with the way that we know how to do it, or it's going to take us a lot of work. So right now, this interval in front of us, 3x plus 2, that quantity times 3x squared plus 4x, and that quantity is to the fourth power dx. So in order for me to be able to integrate this, I would have to expand out that 3x squared plus 4x to the fourth. So multiply that by itself 4 times and then distribute that 3x plus 2. And so that's going to be a lot of work. And so sometimes this method of substitution gives us a way to make integration a lot simpler. So with this example, I'm going to kind of show you how to do that integration by substitution. So what you're looking for is a piece of the integrand that when you took the derivative of is going to look similar to another piece in our integrand. And usually you're going to look at stuff that's inside. Like here, the main piece that's going to be hard for me is this 3x squared plus 4x raised to the fourth power. So I'm looking at inside this parentheses, and I think to myself, okay, let's choose u to be that for now. And sometimes you're going to choose u to be the wrong thing, and you'll find out that it doesn't work, and you'll have to go back and choose something different. But for now, I see that I want u to be 3x squared plus 4x. So choose some value for your substitution, and then we're going to differentiate both sides. So when I differentiate u with respect to x, this is 1 du dx is equal to the integral, or the, antiderivative, not antiderivative, the derivative of 3x squared, which is going to give me 6x. And actually, this is just du. Yeah, so that's 1 du is equal to 6x plus 4, and we integrated that with respect to x, so we're going to write dx. So if I went back in here and I replaced what I chose u to be, I would have 3x plus 2. In here, I would have this u. This would be raised to the fourth power. I don't want dx here because now I'm going to be taking the antiderivative with respect to u. So over here, let's solve for dx and rewrite it in terms of du. So I could do that by dividing both sides of my equation by that 6x plus 4. And if I do so, I get 1 over 6x plus 4 du. I'm going to just rewrite this a little bit more. This is, actually, let's just write it here. So this is du all over 6x plus 4. So I noticed that in my denominator, I have 6x plus 4. If I factor out a 2 in that denominator, I would have the same factor that I have in my numerator up here of 3x plus 2. So let's go back in here. So we have 3x plus 4. I'm sorry, 3x plus 2, all times u to the fourth du all over, I can just put this over 1. So this is all over, pull out a 2 times 3x plus 2. So now doing so, notice this 3x plus 2's cancel. And we're left with something that we know how to integrate. This is 1/2 u to the fourth power du. So this is the same thing. Pull the 1/2 out front. We're going to add 1 to our exponent. So adding 1 to 4, I get 5. Divide by my new exponent of 5. And then I'm going to add my c because it's an indefinite integral. So this is the same thing as u to the 5th over 10 plus c. But my function is in terms of x, and I want x. So let's just go back. We know what u is. U is this 3x squared plus 4x. So here we have 3x squared plus 4x raised to the 5th power, all divided by 10 plus c. And this is our antiderivative of our interval there. So we could always go back and check. We saw if we took the derivative of the antiderivative, we should get back our integrand, which in this case is this. Okay, so let's go through and look at some more examples of the substitution. So in the next example, we have the integral of 1 plus the square root of x. That 1 plus square root of x is all raised to the 1/3 power. And then it's all over the square root of x dx. So we want to choose some value u that hopefully when we take the derivative of and we do substitution, things will start to cancel out and we'll be able to integrate. This is not in a form that we know how to integrate. And in this case, there's no way that I can manipulate this rewriting it to help me. So I'm going to use substitution. You usually think of it as using the inner function. So I'm going to think of it using, let's see if we use 1 plus the square root of x, but I'm going to rewrite the square root of x as x to the 1/2 power. So differentiating both sides of this, I get the derivative of u is 1 du is equal to the derivative of the constant 1 is 0. Plus the derivative of x to the 1/2 is 1/2 x to the negative 1/2 dx. Let's just rewrite this. So du is equal to 1 over 2 square root of x. So just rewriting that x to the negative 1/2, bring it down to the denominator and rewrite it as a radical and then times dx. So notice we can get dx by itself here by multiplying both sides by that 2 square roots of x. So dx is the same thing as 2 square roots of x times du. So let's go back and plug in what we have. So we have now u to the 1/3 power all over the square root of x times dx, but dx is 2 square roots of x du. So we know that we chose this correctly because now when we go and simplify, the square roots of x cancels, and now we just have a function in terms of u. And so now we're looking at the integral of 2u to the 1/3 power du. So bringing down the 2, adding 1 to our exponent. So 1/3 plus 1, 1/3 plus 3/3 is 4/3. Divide by our exponent 4/3. If I'm dividing by my new exponent and it's a fraction, I always tend to just multiply by the reciprocal. So dividing by 4/3 would be the same thing as multiplying by 3/4 plus c. So notice things can simplify a little bit. 2 goes into 4 twice, and so this is going to give me 3/2 u, but we know what u is. Let's go back and substitute what u is in terms of x, which is this 1 plus the square root of x to our new power of 4/3 plus c. So we're looking at the integral of cosine of 2x dx. So in these, if it's not just a trig function, our argument is not just x, we can use substitution here. We can assume that u is equal to 2x, and then we would have du is equal to 2 dx. Let's divide by 2, so I get dx is equal to du divided by 2. So integrating this is cosine of u times du over 2, or du, and I can pull that 1/2 out front. So going backwards, what can I take the derivative of to get cosine? The derivative of sine is cosine, so this would be 1/2 sine of u plus c, which is 1/2 sine of 2x plus c. That's why when you have the integral of a trig function, so let's say cosine of ax dx, this is the same thing as sine of ax over a plus c. Or if we had the antiderivative of sine of a of x dx, well, what gives me the derivative? When I take the derivative, it gives me sine. Well, when I take the derivative of cosine, that's negative sine. So the derivative of negative cosine would give me positive sine. So this would be negative cosine of ax all over a plus c. So knowing that, we can use the following. Let's look at this now, which was a lot more difficult. So we have the integral of 1 minus cosine of t divided by 2, quantity squared, all times sine of t divided by 2 dt. So we want to choose our value to be u. The most complicated part, usually within a function. So if I chose u to equal this 1 minus cosine of t divided by 2. So taking the derivative of both sides, derivative of u, I get 1 du equals derivative of 1 is 0. Derivative of negative cosine is positive sine of the inside, because I need to use the chain rule, t over 2 times the derivative of the inside, which is 1/2 dt. So dt here is equal to I'm dividing, so du all over sine of t over 2, and I'm going to flip my 2 up, so 2 times that. So the integral of u squared sine of t over 2 dt, but dt we just found was times 2 du all over sine of t over 2. So notice what we wanted cancels out. The sine of t over 2 goes away with this. And so now we're just left with the integral of 2u squared du, which isn't too bad to integrate. So bring down the 2, add 1 to our exponent, so we got u cubed, divide by our new exponent of 3 plus c. And then go back and substitute, so we get 2, u is just 1 minus cosine of t divided by 2, quantity squared, all over 3 plus c. This should have been quantity cubed, because that's a 3. So let me show you a case where substitution doesn't work right away. So noticing here, our example is an integration of x cubed times the quantity of the square root. Under the square root is x squared plus 1, and then we have dx. So if I chose what we've been doing, that inner function in this case would have been x squared plus 1, and I take the derivative of that, I notice that it's not going to undo that x cubed. But it's going to get it in a form that we will be able to integrate. So again, let's just choose u to be this, what's underneath the radical, which is called the radicand, x squared plus 1. Differentiate both sides, we get du equals 2x dx. So dx in this case is du over 2x. So the integral here of x cubed is the square root of u times du over 2x. So it simplifies a little bit, but we're still left with an x in our integrand. So this is the same thing as the integral of 1/2 x goes into x squared, x cubed, x squared times the square root of u du. So we have a problem because we want this all to be in terms of one variable u. So go back up into our substitution and notice that we can solve for x squared in terms of u. We have an x squared in here. Let's solve for x squared in terms of u. So basically, let's just get x squared by itself. We could subtract 1. I know x squared then is equal to u minus 1. So let's go back in and let's substitute what x squared is in terms of u. And then we're just going to have a function in terms of u, which we wanted. You can bring that 1/2 in front of the integral if you'd like. So 1/2 the integral of x squared, the x squared we can rewrite as u minus 1 times the square root of u. I'm going to rewrite that square root of u as u to the 1/2 power du. So now we can distribute that u to the 1/2 power to each term inside the parentheses. Using rules of exponents, I'd be adding my exponent. So, excuse me. U to the 1/2 times u is u to the 3/2 power minus u to the 1/2 power du. So now it's in that form that we can integrate. So let's bring down the 1/2. Just do it here. So the antiderivative of u to the 3/2, we're adding 1 to 3/2. So 3/2 plus 2/2 is 5/2. Dividing by 5/2 is the same as multiplying by 2/5, reciprocal. Minus, so adding 1 to my exponent of 1/2, so 1/2 plus 2/2 is 3/2. dividing by 3/2 is the same thing as multiplying by 2/3. And then I'm going to add some constant c. So let's kind of rewrite this. At the same time as we're rewriting it, let's substitute in what u is. You know u is that x squared plus 1. So this is equal to 1/2 all times. Actually, let's distribute the 1/2 because that 1/2 is going to just cancel with the 2's in our numerator. So if we distributed that 1/2, we'd have 1/2 times 2/5 is 1/5 u, but u is x squared plus 1 raised to the 5/2. That 1/2 times negative 2/3. The 2 is going to cancel, leaving us just with negative 1/3 u, which is x squared plus 1 raised to the 3/2 power plus c. And if we want, we can rewrite those with the radicals. Just because the integrand was with radicals, I might just go back and rewrite this. So this is 1/5 the square root of x squared plus 1 raised to the 5th power minus 1/3 square root of x squared plus 1. That x squared plus 1 is cubed plus c. So our next example is the integral of the natural log of the square root of t all over t dt. If you ever have a natural log in there, we don't know how to integrate natural logs. Natural logs is usually what you're going to choose to be u to be. I noticed that I can first use properties of natural logs to rewrite that natural log of the square root of t is the same thing as the natural log of t to the 1/2 power. Using properties of logs, I can bring that exponent down front and rewrite it as 1/2 natural log of t. So let's just go ahead and do that. So this is the same thing, and I can pull that 1/2 out front. So this is 1/2 the integral of the natural log of t all over t dt. So if there's a natural log as part of your function, choose that piece to be your u. And so if I took the derivative of both sides, I get du equals, well, the derivative of the natural log of t is 1 over t dt. Multiply both sides by t, I get dt equals t du. So I have 1/2 the integral of the natural log of t, which we chose to be u, all over t. Dt, though, was t du. So notice that things cancel like we want. The t's go away, and now we have an integral with just u in there. And so finding the antiderivative of u, bringing down the 1/2, we would add 1 to our exponent, so u squared, divide by our new exponent 2 plus c. So this is the same thing as 1/4 u, though, we chose to be the natural log of t. This whole thing is squared plus c.